Hi, this project is about concurrent face emotion recognition. So it's basically to classify face expressions efficiently with the use of pattern recognition. The primary objective is to give a reliable, distributed, and efficient classification of face expressions by making use of open source frameworks such as TensorFlow and feature extraction and feature selection strategies. And we implement here a face expression recognition using both convolutional network and a few image preprocessing steps on a Kaggle dataset. And face expression recognition finds its applications in human interaction systems, data-driven animation, interactive games, and neuromarketing. And the use cases for this project will be to identify one of these expressions for the image: angry, fear, happy, sad, disgust, surprise, and neutral. Coming to the project details, we have a training dataset of around 28,709 images and public test and private test images as well. And then the project dataset is FER 2013 dataset. The current state-of-art accuracy for the face expression recognition, as per what I've researched with a couple of research papers, is 70%, and what we have achieved is 60 to 65%. And the tools used are TensorFlow. And coming to the flow chart, the first step starts with image cropping and intensity normalization, and then a set of CNN models, and then a TensorFlow which will decide the best model. So architecture phase 1, it has the face acquisition, that is face detection and head pose estimation, and facial data extraction and representation. So once the face is identified, those facial changes that are caused due to the facial expressions need to be captured. And then image cropping, we want to remove the unwanted data from the images. So because for our expression recognition, the part that is most important is just the region between eyes and from forehead to chin. So our input image of 48 cross 48 pixels is cropped to 32 cross 32 pixels, and then the intensity normalization so that it reduces the complexity, the problem the classifier needs to solve for each expression. Because of the variations in the image brightness and contrast, it might become complicated, so we basically level it. And then in the phase 2 of architecture, we have a convolutional neural network, which is the primary thing in our project. So it has 9 layers. The first layer is a convolutional type. So it takes an input of 32 cross 32 pixel images in a batch of 128, and it uses 64 9 cross 9 filters and outputs 64 activation maps of dimensions 24 cross 24. And the second layer is a max pooling layer, and it is performed on a window of 3 cross 3 with strides of 2, and it maintains the dimensions of the output images as 24 cross 24 itself. And in the third layer is a local response normalization, and fourth layer is again convolution type, which uses 128 5 cross 5 filters with one stride. And the fifth layer, again local response normalization is performed. Sixth layer is a max pooling layer, and which is performed on a window of 3 cross 3 with strides of 2, and 2 fully connected layers which will reshape the matrix into a single matrix vector by using 384 and 192 neurons respectively. In the ninth layer, we have a softmax layer, and that classifies all the images into 7 classes. That is, 0 represents angry, 1 represents fear, 2 represents happy, 3 for sad, disgust, surprise, neutral, and with their corresponding probabilities. So these are the parameters in our model. So we have around 27 million parameters, and it shows how many parameters for each layer as well. So the basic algorithms we used here are convolutional neural network architecture, and that is decided based on which gives the best accuracy. And this is how we distribute our training the data set, and that's how we achieved a less reduced training time. So the comparison of local GPU and distributed GPU and with distributed 32 GPU. So here we show the comparison between how efficient and how much time the training time will be less depending on what approach we adopt. And this is the interaction diagram for our convolutional neural network, how our code components, how our classes are interacting with each other. And basically the modules we have, again I repeat, is pre-processing, that is image cropping and intensity normalization. Then the input is for the CNN, convolutional neural network, and where it will output a single label number that expresses one of the 7 basic expressions. And here one of the main component is also TensorFlow, which is used for hyperparameter tuning, which is again distributed in our project so that we achieved less training time. And the class diagram for our convolutional neural network is shown below. And if you see here, the precision we achieved is 65%, and when we start training the dataset, the loss, this is how the loss is shown. So if you see here, running the evaluation model on several checkpoints has clearly indicated the rise in the precision percentage as shown in the left hand side of the image. And then the checkpoints are created after every 1000 executions. So the first checkpoint resulting in the precision percentage of 14%, and after 20,000 batch trainings we're able to achieve 65% of accuracy. So this is how the images are being cropped, and how exactly the convolutional neural network has started extracting the features and how it works on them. So the performance metrics are basically, the training batch size is 128 images, and our target is to train around 100,000 such batches. So the initial learning rate started with 0.1, and then the learning rate changes by decay factor of 0.1 after a complete execution of 350 epochs. So epoch is nothing but one full data set, which is roughly 29,000 images. So and we're able to run the current implementation on a quad-core Intel CPU till about 20,000 training steps, and that took 8 hours to train, and it's just 8 hours to train, and we observed that there is 65% accuracy after evaluating the model. So we deploying this model on a distributed GPU version yielded the less training time, and of course there is not a difference in the accuracy but in the training time. So it's basically 100 examples per second on CPU versus 400 examples per second on a GPU. So, thank you. Coming to the presentation of our project and then the demonstration. So what we have here is the code base for our emotion recognition. So here I'll show you the dataset firstly. So FER2013.CSV is a dataset. It has so it's basically used to train our model, and then so the dataset is shown like this. So it has the image representation here along with the corresponding emotion. So this emotion is nothing but the label. So let's say 2 represents happy, 3 represents sad. And then FER2013.bin is the binary representation of this data set, and we converted that based on this script. So uint8 to binary.rb. So basically our data set is FER2013.CSV, and then the converted to FER2013.bin. And now we would train our convolutional neural network. So based on this script, FER 2013 underscore train.py. So let's start training our model. So this should start training our convolutional neural network based on the images what we have seen in the data set, and also it has also the emotion labels. So our model will start understanding that. So if you observe here, the loss started decreasing, and then we have to evaluate our model. So how well our model is trained. So we need to know how much accuracy our model will obtain. So we evaluate our model based on this script. So this script, FER 2013 eval.py, will evaluate a convolutional neural network model, and it is evaluated based on a data set of images which has a correct label in one of its columns, and then the output of the model is compared against that of the label of that image, and then it finds out whether it predicted correctly or not. So we would execute this FER 2013 underscore eval.py. So for the purpose of this video, I can show you that precision percentage here we obtained is 65%, and then we would have to let's say I will show you the image, and then when I pass that image as the input to our model, it will detect the correct label for it. Let's see how it does. So let's say these are the images we have right now. Let's say this image 6, he's basically angry. So let's pass this image as the input to our convolutional neural network and see what it predicts. So I'll pass the image number 6 here. Awesome. So we got the output as angry. So our model predicted that he's angry, and it's correct. We'll check for one more example. Let's say this one, he's basically sad. Okay, so I'll pass the input as 3. Wow, that's correct. So that's how we achieved an accuracy of 65%, and then also a very less training time. So yeah, thank you.